So we start the next lecture that is on non-linear programming. So we have seen linear programming, discrete models, and now we extend what is the workforce of optimization, that is non-linear programming. Right? It is actually one of the most useful things because now, for instance, with all this deep learning stuff, it relies a lot on non-linear programming. Okay, so yes, this is the outline. It is a long lecture, so it will take us a few hours. So the thing is, we have the typical optimization problem. So minimize something subject to some inequality constraints and equality constraints. What is different is that now the f function, so the function to minimize is non-linear, and the inequality constraints and the equality constraints may also be non-linear. So everything can be non-linear. And just a reminder, the linear things are those ones that can be expressed in this way. So something is linear if it can be expressed as a set of coefficients transposed the vector. So they cannot be expressed in this way. Okay, so here are some examples of linearity, of non-linearity. So here you have a quadratic form, and here you have the norm 1. Do you know the different norms? So norm 1, norm 0, norm p. You do? You don't. Okay, so let's explain them. So you have the norm of a vector. So the norm of a vector typically, let's put it this way. So we don't care if it is a square or not. So it is just a matter of taking the square root. So let's put it a square. And very often it is defined as an inner product. So you need a definition of inner product to define, like this one, to define a norm. And when you are dealing with vectors, the most typical inner product is this one. So X transpose X. It is not the only one, but it is a very common one. And if you expand this, so this is the first component squared, second component squared, up to the p, or not p, n component squared. Okay, good. And this is called the norm 2. Okay, so what if we define the norm 1? The norm 1 would be the sum, this sum would be expressed this way. The sum of all components of the component squared. So the norm of 1 would be the same, but now taking the absolute values. So here we have exponent 2, this exponent 2, and this exponent 2 has to do with this 2. And here we don't have, if you want, you have an exponent 1 that has to do with that one. And then you can generalize that. And then you can say, okay, so why not, why using 1 or 2? Why can I not use 3, for instance? So you can do 3 or any one in, and say the norm p will be this, sorry, the p goes down, the p goes down. So it will be the square root of p or the sum i from 1 to n x to I p power. And now you have this p goes there. And this p can take any value. So p can be from 0 to infinity. So, and then it has some interesting properties. So, for instance, for p equal 2, we have the standard, this is the Euclidean one. This is the L1 norm. And for P larger than 1, it is kind of a mixture somewhere between L1 and Euclidean. And for P equal between 0 and 1, so if P belongs to 0 and 1, it tends to promote sparsity. So when you use it as a penalization in some loss function, it tends to make that X takes a sparse value. And you can see it somehow for the 0 mode. So X 0. So it is the limit P goes to 0 or this limit. And it can be shown that it is the maximum array of this set. So you take, well, you see this xi, that is the component I of the vector f. You take it in absolute value, you take the maximum. And the reason why is that it is because if you consider this sum, only the maximum survives. So when P goes to 0, only the maximum survives this sum. All the rest, they tend to go to 0. Okay, so very good. So here we have the L1 norm. So the L1 norm is, for instance, in which one? Lasso. This is Lasso. So you tend to penalize with L1 norms. If you don't say anything, it is understood it is the L2 norm. So here we are not putting the 2 down. Then the constraint is again a quadratic form. So it is non-linear. So you cannot write it in this way. You cannot write it this way. So it is a non-linear constraint. And the equality, you can put non-linear functions, you can do whatever. So these are examples of non-linearity. Very good. Then we need to introduce convexity. So actually today we will only talk about convexity. So let us first define a convex set. So you say that a set is convex if you take any 2 points in the set, you join it with a line, with a segment, and then the segment is fully contained in the set. So this is this segment. So if you take a lambda between 0 and 1, and you do lambda x plus 1 minus lambda y. So for lambda equal 1, you are at x, because this term is 0. For lambda equals 0, you are at y. And for lambda between 0 and 1, you are somewhere between x and y. So if the full segment is contained within the set, then you say it is a convex set. And then we can also define a convex function. So we have a function, and you say it is convex if this condition is fulfilled. So for any point in the segment, you evaluate the function, and the function is always a smaller or equal this thing. And this thing is a segment in the images of f and the image, so the image of f and the image of y. So for instance, here you have a convex function. Here you have a non-convex function. So for this convex function, if you take any 2 points, this one, and you join by a segment, the function is always below the segment. Here it doesn't happen. Sometimes it is above the segment, sometimes it is below the segment. So if it is always below the segment, it is convex. And also you can think of it as this is the set. So the part, the region of the space above the function is the space, is the set, and then the segment is fully contained in that set. So it is the same definition as this one. Okay, so Any question up to here? No? Convex functions? Is it the first time you find convex functions? But probably not for you, for you. No? Okay, good. Then, why convexity is important? Because if a function is convex, then there are many nice conditions that save you a lot of time when doing when optimizing it. So the main property is this one, that is every local minimum is a global minimum. So if you find a local minimum and the function is convex, then you know that minimum is global. And then this is a consequence of that. So if f is convex and it is differentiable, and you find a point for which the gradient is zero, then that point is the global optimum, because this is a local optimum, or it is a saddle point at least. It could be saddle or optimum, but then it is optimum. So for convex functions, they cannot be saddle points. So once you find one, you stop looking for other ones, because you know that is the global one. And then first order optimality is sufficient. So it is somehow what we have said there. So if f is convex, then and you find this a point for which the gradient is zero, that is necessary, but it is also sufficient. So in general, in the general setup, it is a necessary condition, but for convex functions, it is also sufficient. So if you find x star such as the gradient is zero, then that is a minimum and cannot be a saddle point or whatever. So in general, for non-convex functions, this condition is necessary, but and points that satisfy this condition, they are called stationary points, but they are but they can be minima, they can be maxima, or they can be saddle points. But if the function is complex, they can only be optimal, so minimum or maximum. Okay, then if the function is convex, then the optimizing it can be solved in polynomial time, so that finding the optimum can be very, very fast. And there are methods that are guaranteed to converge to the minimum. So those are very nice properties. So if the problem, on the contrary, if the problem is non-convex, then these methods, they converge to local minima. So they converge to suboptimal points. And okay, yeah, so if you don't have convexity, functions in general, they have multiple local minima, you converge to one of them. There are saddle points and plateaus, so there are some regions in which the gradient is zero, but the function doesn't improve. Do you know what is a saddle point in the function? You do. Okay, very good. Then because you have many local minima and these algorithms converge to local minima, then for non-convex functions, the solution depends on the initialization. So you start somewhere and you go to the local minimum, and if you start somewhere else, then you go to a different local minimum. Examples of convexity: x squared is a convex function. The exponential is a convex function. The logarithm is the opposite. It's a concave function. The norm, the Euclidean norm, is convex. Somehow the Euclidean norm is kind of similar to x squared, right? This is the L1 norm inverted. So this is concave because this one is convex. So this has to be the opposite. The maximum with zero is also convex. The square root is concave. And here I'm making some more comments, but Any question? No? Okay, then more examples of complex problems. These are very, very important. All of them are very important complex problems. So the first one is least squares. So least squares, that is typically formulated this way, this is a convex function. So the objective is convex. If you find the minimum, it is the global minimum. And it comes from a quadratic function, and typically you either you solve it in closed form. So there is an analytical formula that tells you what is the minimum at once without any iteration. We saw that one at the beginning of the course, or you use some gradient-based methods that we will study in this lecture to solve it. Linear programming, this function is convex, and the constraints are also convex. So the simplex that we saw is one way of looking for the optimum. But for instance, one of the methods that we will study in this lecture, this interior point, will also be another method. But the problem is convex. Once you find the optimum, then you're done. Lasso regression is like the least square regression. So plus some penalization on X. So this penalization on X that is using the L1 norm tries to promote solutions that do not have many active components. So these are called a sparse solution. So the sparse solution is you have a lot of zeros, a few different from zeros, and then again a lot of zeros. This is convex, but it is not. It is non-smooth because this penalization term is not differentiable. In general, all these are goal functions in which you have two terms. This structure is very common. So you have what is called a data fidelity term. So your measurements are B, and you are looking for a model X such that when you measure, it gives the same measurements as B. So this is the data fidelity term. And this is a regularization term. So this regularization imposes something on the kind of models you want to solve, to find. And for instance, this one is solved with proximal algorithms that we will also study in this lecture. Then you have support vector machines. Support vector machines is a classic, you have seen them, right? Classification. So in classification, this formulation is assuming that the labels are -1 or 1, and then you want to minimize this thing. So this thing is, you recognize, this is the regularization term, and this is the data fidelity term. And this C controls how much one is more important than the other. You always have the same structure also. Here, lambda controls how much more important is the regularization with respect to the data fidelity. And there is a logistic regression. Do you know logistic regression? Yeah, you do also? No? Logistic regression is, let's see if I can find, okay. Let's put it this way. So with only one variable. So with only one variable, let's say that you are given a set of x and y's. So for instance, this could be the probability of dying, for instance. And this is age. And this is whether someone has died or not. So this is, for instance, you have different ages, and here we will encode this person of this age didn't die, this one didn't die, this one didn't, but this did, and so on. And then what you have is you can represent this y, and you would have few numbers here, few numbers there. Say, but this cannot be seen, right? let's put the axis here. Let's put the axis here. So it is minus 1 or 1, this is 8, and then there must be some function that at some point there is a high probability of dying next. So you can express the goal function in this way, and this goal function is convex again. Okay, so this would be 8, and this would be actually can be a vector. This is also a vector, and here you recognize an inner product actually. Yeah, and this x is the set of coefficients of the regression. Very good. So all these problems, all of them are very important, and all of them are convex. So once you find an optimum, it will be a global optimum. And here you have also very important problems that are non-convex. So training a neural network is non-convex, and the non-convexity comes mostly through the activation functions. So the activation functions make the problem to be non-convex. And that means that it will have many local minima and many saddle points. And k-means that you also know. K-means is also a non-convex problem. And the non-convexity comes from the assignment of every point to the centroid. Matrix factorization, this problem may be new for you, is it? So it is, you are given a matrix, and you want to approximate this matrix by the product of two other matrices. And then this F is the Frobenius norm. So it is like the Euclidean norm for matrices. So it is summing all the elements in the matrix squared. So this bilinear structure, so this product two matrices, make the problem to be non-convex. And for instance, in recommendation systems like the Netflix problem, that is the problem they are solving is this one. And then you have a sparse PCA. So let's say that you have a covariance matrix, and you want to find the direction in which this quadratic form is maximum. That is the goal of PCA. And then so this is a standard PCA with this constraint. And this one is looking for the X that has at most, so the maximum value. Actually, I did it wrong. I told you that it is here, the norm 0. I told you it was the maximum. It is not that. It is not that. I'm sorry. Very sorry about that. It is the count. So it is the count of non-zero components. X, I, different from 0. So it is this count. So you count how many elements are different from 0, and that is the 0 norm. So you want at most k components to be non-zero. Okay, and this is everything involving the 0 norm is combinatorial, because you have to try all possibilities to see it. Okay, so the first component is not 0, the second is not 0, the third is not 0, and all possible combinations of those. Then combinatorial optimization, like the traveling salesman and the knapsack. So they are the variables are naturally discrete, and the problem is combinatorial. And phase retrieval and blind deconvolution, the formulation is this one, and looks very much like the least squares, but there is a difference. Here you are only measuring the absolute value of this matrix. And then that absolute value makes the problem non-convex. Okay, any question? No? Very good. Then you can have constraints. So let's say that you have a convexity a convex objective function, but now you have a constraint. So if the feasible region is convex, then the problem stays convex. So as long as the feasible region is convex, the convexity is not broken. And then the Karuskul-Tucker conditions, they are again sufficient for optimality. So normally they are necessary, but here, because the problem stays convex, so it is also sufficient. And here you have something that is a property of convex functions that is very much used in many problems. That is this Jensen's inequality that somehow is a generalization of the definition of convexity. So let's go back to the definition of convexity. So we have this one. So if you make a linear combination of 2 points, that is always a smaller or equal the linear combination of the images. Okay, so then this is what we have here, but for any x, for any m points, so we have generalized from 2 to m. So if you make a linear combination of points, then the function evaluated there is always smaller or equal the linear combination, the same linear combination of the images. And these lambdas, they are in some probability simplex. So probability simplex is this one. So probability simplex is this one. So it is the set lambda 1, lambda 2, lambda n in R such that the sum all of them is equal to 1. So it is a probability distribution. So that is called the probability simplex. Very good. So and this probability simplex can be scaled. So I can multiply by delta m. So it is not the sum is equal to 1, but the sum is equal to delta m. And so in summary, if you have a convex problem, then a local optimum, local minimum is a global minimum. And for non-convex problems, it is not guaranteed. The stationary point is always optimal. So the point at which the gradient is 0, it is always an optimum of that. And there are strong guarantees that the algorithm will converge to the global minimum, while for general problems, they converge to local, or you use some heuristic to find something useful, but you are not guaranteed to go to the global minimum. And for convex problems, you go very quickly to the global minimum. And here you may go much more slowly. Okay, very good. Then more properties of convexity. So let's say that you have a number of convex functions, and you make a linear combination of them with all the weights larger or equal to 0. So the linear combination is also convex. And if some of them are negative, so then the convexity is lost. Then affine function. So affine function is a generalization of this one. So it is this one. So x is a convex function. So the identity is a convex function. And A transpose x plus b. This is the affine function. So the affine function is convex, right? It's also concave. So if you think of convexity and concavity as something that shown here, so we said this is a convex function, the opposite is a concave function, but the affine transformation is flat. So if it is flat, then it is concave and convex at the same time. Okay, so affine functions are convex and concave. The composition with an affine mapping is also convex. So if f is convex and you have some variable, you apply an affine transformation and then go through f, then the result is still convex. Computing the maximum preserves convexity. So you have a set of convex functions and you compute the maximum at every point. So that is convex still. Then the perspective function it keeps convexity. So let's say that f is convex, and then you make this transformation with t larger than 0. Then g, the new function, is convex in this vector. And the composition rule is also keeps complexity in this way. So let's say that you are composing two functions. So first you apply g, then you apply h. H is convex, and so g is convex, h is convex, but there is another constraint that is non-decreasing. So if it is non-decreasing, the composition keeps convexity. And here it is a little bit more surprising. So G is concave, but H is convex and non-increasing. And then the result is convex, but you start from a concave function. Then you have a sequence of convex functions, and you compute a new function that is the limit when this n goes to infinity of this sequence. Then f is convex, but for that you need that the limit exists and it is finite. And some operations that destroy convexity. So the negative of a convex function is not convex. Actually, it is the opposite, it is concave. Multiplying two convex functions may be or may not be convex. Division, the same. The composition in general, it is not convex. We have seen that depends on the monotonicity. Okay, so there are some monotonic constraints. And the minimum is not convex. Then, let's say that we have a convex function. So if you have a convex function, then this condition is always met. So actually, it is also a necessary condition. So it is not only so it is necessary and it's sufficient. So a function f is differentiable if and only if for every point x. So this part here is the tangent plane below the graph. So it is the tangent plane. Okay, so this thing here is the tangent plane at x. Okay, so you have your function, you put a plane that is tangent to x. And then what this is saying is that the tangent is always below the graph. So you have the function and then you have your tangent, and the tangent is always below. So this is the tangent plane or tangent hyperplane. And then the hyperplane is always below the graph. There is another characterization of convex functions. So if the function is twice differentiable, then it is convex if and only if the Hessian that we already introduced, I think, is always positive semi-definite. So positive semi-definite means all the eigenvalues of this matrix are always larger or equal to 0. And this is one of the properties that some kind of algorithms that we will also see, they are exploiting. Then what about constraint optimization? So let's say that you have an objective function that is convex, inequality constraints that are convex, and equality constraints that are affine. So overall, this problem is complex, and the corresponding conditions are sufficient that in the general setup they are only necessary. So a point can be an optimum if they fulfill these conditions. But for this setup in convexity, then they are also sufficient. So once you find a point that fulfills these conditions, you are done. You don't have to check if it is an optimum or not. And many libraries that you are using, they exploit this structure of convexity to guarantee for global solutions. We can define even more complex or give further definitions of convexity, what is called a strict convexity, strong convexity, and uniform convexity. This one we will not see. They are more complicated, but these two, they're kind of easy. So this one, the strict convexity, is this one. It is the one that we have seen so far, and it guarantees that there is only one minimizer of that point, of that function. Then you have the strong convexity. The strong convexity, you recognize here the hyperplane. So this is the tangent hyperplane. And if your function is larger than the tangent hyperplane, plus something that depends on the distance of between x and y, then it is all, this is called a strong convexity. So a function is a strong convex if there exists an n such that for every point this is fulfilled. And if this is fulfilled, then the convergence rate to the minimum is it's pretty good. It is said to be linear instead of sublinear. So all these gradient methods that we will study in the next hours, all these gradient methods, they go very quickly in a linear way to the minimum, and in general they go in a sublinear way. So they go more slowly, and somehow this is explained here. So this is the linear convergence. So k is the iteration number. So these methods we have not studied yet, but we will see in the next hours. Gradient descent, Newton's method, accelerated gradient. For convex problems, they converge in this way. These are sublinear convergence, so they converge relatively quickly, but here what it means is that it can be even quicker. So it can converge even quicker because of the strong convexity. We have seen a few problems here that we said, well, for instance, we have seen a few problems that we have said, okay, these are very important problems. And what we can do here is you have a non-convex problem and you relax them. So for instance, the sparse regression uses a zero and an L0 norm. So just counting how many elements are different from zero. And this is very expensive because it is combinatorial. But then what you do is a convex relaxation. So you substitute the L0 norm by an L1 norm, and now the problem becomes complex. You go very quickly to the optimum, and then somehow you try to refine and see if you can find in the neighborhood some solution of the original problem, the sparse one. This is semi-definite programming relaxations for MaxCat. MaxCat is a problem of, let me see if I can find a nice picture of it. So look for MaxCat graph problem. So it is finding, for instance, here probably. So you're given a graph and you want to separate this graph into different pieces such that the edges that you are cutting are, so the weight of those edges is maximum. So this max cut problem is I think it is a combinatorial problem too. So it is NP hard, I think. Can check that. So this max cut is a combinatorial problem. This max cut somehow it is related to community detection. So if you think of a social network like Facebook or LinkedIn or whatever, you think every node is a person, and then all the connections that it has with different persons. And that might be very likely kind of community. So all these people within this community, they are very much linked to each other, and the same here. And there are very little jumps from one to the other communities. So the max cut problem or the min cut problem, which is equivalent, it is okay, I will try to separate these two communities that are very weakly connected. And that problem is combinatorial, but then you can relax it to something that is convex. And again, this mixed integer programming, mixed integer is a program or a problem in which you have integers and you have continuous value functions, and then you can do a linear or a convex approximation to the problem. So the goal is always, because convex problems are so easy to solve, then I will try to convert non-convex problems into convex ones. And then this is the gallery of methods that we will study here. So not only for convex problems, they behave better if the problem is convex, but not necessarily they are only for complex problems. So we will study all of these. So this is the gallery of methods. And the one gradient descent, do you know already gradient descent from other courses? Yeah, very good. And then we will study many others that are very, actually ADMM is very popular. All these sister approaches, they are also very important. Interior point methods, there are many. And here there are some properties of these families. So there are some families that are based on gradient, these proximal functions, the composition. For the moment, you don't know what they are, but you start to see their properties. So do they need a gradient? Gradient-based methods, they obviously need a gradient, but proximal methods, they don't need a gradient. And yeah, these are the ones that need or don't need a gradient. Then do they apply to convex problems, to non-convex problems? You see that some families, it's the composition or interior points that particularly are adapted to convex problems, but they cannot work with non-convex problems. Then can they handle constraints? And some examples of problems that are typically solved with these methods. Any question? No? Okay, so then more properties on convex and convexity and this nonlinear programming. So we have clearly separated convex from non-convex problems because of this property, because a local minimum becomes a global minimum. We will make some points, some remarks on numerical conditioning. So numerical conditioning has to do with the following. So how sensible is the solution to small changes in the input? So if you change the input a little bit, so that the first initial point, does it converge to the same minimum? And then poor conditioning leads to instability, and good conditioning always goes to the same, almost the same minimum. And then preconditioning the problem with this Jacobian or Hessian preconditioning will be very important for these Newton type methods. We will see all this later. The other thing is regularization. Regularization has already appeared. So regularization is this kind of penalty functions that we have. Some examples here. So this kind of regularizations, this one here, so that you penalize some properties of the solution that you are looking. Here you are trying to penalize the node L1 node, here the L2 node. So all these penalizations, they try to impose some properties on the solution. So yeah, with L1 node, it's called Dassault, with L2 node, it's called Reach. And they tend to help in this conditioning. So imposedness is the same as for conditioning. So these penalizations they tend to help conditioning the problem. And they are also used to avoid getting too much time to training data. So in all these inverse problems, machine learning help very much. Do you know what inverse problems are? No? Okay, so inverse problem is the following. So you have, let's say, some input data X that goes into a system. This system can be whatever, so non-linear, linear, they can be whatever. And your mechanism Y. So given the Y and the H, yeah, given Y, the inverse problem is of this X. So what was the input to the system? Such that the observations are what I have to say. What are the inverse? And typically you can solve it like this. Minimum of Y minus H applied to this. Okay. And then this is sparse optimization, in which you try to focus on solutions that have many zeros. And then L1 node promotes sparsity, and it is a convex, so it is a good one. The L0 node also promotes sparsity, but it is not convex, and it is actually combinatorial. It's a very bad node for solving it efficiently. And between 0 and 1, these LP nodes that I presented above, these LP nodes, be between 0 and 1, they also tend to promote the sparsity. I don't think they are. I think the first one that is convex is And compressed sensing is a signal processing technique that exploits this actually compressed sensing. The original computation is a signal. Variable selection, for instance, if you want to make a regression, you are given 1,000 variables, you want to make a regression, but with only a few of them that are the most explanatory ones. Then you use these sparse optimizations to find which ones are the good ones. Very good. No question? Okay, so then we start here.